This is going to be our first of, I'm going to air quotes, 3 lectures on transient analysis of first order circuits. And the reason why I'm not necessarily calling it 3 lectures is because usually I actually wind up covering all the material by the end of the second lecture. And then that third day is just spent doing a lab assignment and working the in-class assignment. Okay. So let's first talk about what a first order circuit is. A first order circuit is a circuit that contains a single equivalent energy storage element. Okay. So what I mean by this statement is that if there are multiple inductors in the system, they can be combined into a single equivalent inductance. Similarly, if there are multiple capacitors in the system, they can be combined into a single equivalent capacitance. However, it can't have capacitance and inductance. That would be a second order circuit, which is beyond the scope of this particular class. But for those of you who get to suffer through circuits 2 with me, we spend a good long time figuring out how those guys work. Okay. So I have described what a first order circuit is to you all, and I believe a way that you can reasonably understand. So now let's talk about what transient analysis means. So transient analysis is the analysis of a circuit or system as it is undergoing a change. Okay. So we are going to look at RL circuits, so circuits containing an equivalent resistance and an equivalent inductance. And we're also going to look at RC circuits, circuits containing an equivalent resistance and equivalent capacitance. And we're going to learn how to do the transient analysis of both. So let's first start by looking at an RL circuit. So let's say that I have something like this. I have some current source IS. Here, I'm going to draw a switch. I have 2 terminals. I'm going to put a short here. Here, I'm going to have some resistance R. And over here, I'm going to have some inductance L. And the R and L here are representative of an equivalent resistance and an equivalent inductance for a larger circuit. The reason why I'm pointing that out is because we're going to derive things for this simplified circuit, but we're going to be able to apply them for literally any circuit containing resistors and inductors. Okay. So giving myself a pair of terminals here, and what's going to happen in this circuit is that at t is equal to 0, our switch is going to change states, meaning that it is no longer going to be connected at position A. It will now be connected at position B. And so effectively, our current source is being disconnected from that network containing a resistor and an inductor. Okay. So if we assume that the switch has been closed for a very long time before our switch changes state, we are going to start off at a DC steady state condition, right? So if I were to plot, let me label this here. IL as a function of time. We're going to talk our way through things here. So this is IL as a function of time, and this is my time axis. So for all points in time prior to the switch changing states, we are at a DC steady state condition, right? So all the way up to t is equal to 0. We are at DC steady state, okay? So what do you guys believe the inductor current will be at all points in time, all the way up to t is equal to 0? Yes, exactly right. So when we're at DC steady state, our inductor is going to look like a short circuit because we have a DC circuit here. And so all of the current IS will flow through the inductor, and that will be the inductor current for all points in time until our switch opens up, right? So we're going to have something that looks like this. We have a constant amount of current up until time t is equal to 0. Now, let's go a long time into the future. Okay. Actually, before we look at what's happening a long time into the future, let me talk about what's going on here, right? So if our inductor has some current flowing through it, that means the inductor has some amount of energy stored, right? Because the energy stored by an inductor is equal to 1/2 times the inductor value times the current squared, right? So we have some fixed amount of energy stored in the inductor. When that switch changes state, what is going to happen? The current source is being disconnected from the inductor. So we're not feeding any more energy into that system. So what we will see is that the inductor is going to distribute its energy to that resistor, which will convert it into heat over time, because that's literally all a resistor is capable of doing. So we should see that the inductor is transferring its stored energy to the resistor, and as that energy gets converted into heat, the current flowing through the inductor is going to go towards 0. So at a very long time after our switch has changed state, we should expect to see that all of the energy that was stored in the inductor at t is equal to 0 has been transferred to the resistor and converted to heat, so that our inductor current is now at 0 as well, right? We have no more electrical energy in our system. It's all been transferred to heat. So for t is equal to infinity, and what I mean by infinity here is just a really long time after the switch has changed state, we see that our current has decayed down to 0. I'm going to put a little thing here. So for all t greater than infinity, we are at a DC steady state condition again. Right? Just happens to be that it's a condition where everything is 0, but it's still a DC steady state condition. So this bit in the middle here is our transient condition, where the circuit is undergoing some amount of change. Okay? And so it's our goal to figure out a mathematical model to describe what's happening during this transient condition. Okay. So a couple of things here just really quickly. We have determined by inspection that IL of 0 minus was equal to the current IS. And really that's true for all points in time up to 0 minus. We also found that IL at infinity, a long time after the switch had changed states, our current had decayed down to 0. And now we're trying to figure out what happens between those 2 points in time. So during the transient condition, transient starts with a T, not an F. So 0 plus is less than T is less than infinity. Our circuit looks like this. Here's R. Here's L. And here's IL of T. So what I'm going to do is I'm going to wind up writing a Kirchhoff's voltage law equation. So I'm going to explicitly state here that this is the polarity of my inductor voltage. And this is the polarity of my resistor voltage. And I've chosen these polarities so that my current IL is flowing into the positive polarity terminal of each of those elements during the transient condition so that I don't have to worry about weird negative signs and stuff like that. So if I write a Kirchhoff's voltage law equation, I can see pretty easily that VR plus VL must be equal to 0 during the transient condition. I can express both of those voltages in terms of that common current I that's flowing around that loop on the right-hand side. So for my resistor, I simply have Ohm's law that describes that relationship, right? V is equal to I times R. So I could call this R times IL of T. The voltage drop across an inductor is L di by dt. And this is equal to 0. So what I have here is a homogeneous first order differential equation. I understand that not all of you have yet taken Math 245 and things like that. So we are just going to think about what a possible solution to this equation would be. So effectively, what I mean by that is we are trying to find some mathematical function to substitute in for our inductor current IL of T, such that the function multiplied by some constant, which happens to be our resistance, plus the derivative of the function multiplied by some constant happens to equal 0. So I need a mathematical function where the function plus the derivative can possibly equal 0. Go. Exponential, absolutely. So we are going to make a very educated, and as it turns out, correct guess that IL of t will be of the form A e to the st. If we substitute in this guess for IL of t, we will find that we have R times A e to the st plus SL AE to the st is equal to 0. And now I'm just going to do a little bit of algebra here, right? So I'm going to pull out my factor of A. That's a common factor on both things. So I will have R plus SL times times E to the st. Is equal to 0. And so now we're going to talk about the different ways that this equation can be equal to 0. So the most obvious way is that if A is equal to 0. So A is equal to 0 is a solution, but it is a trivial solution because it effectively means that we started with no energy stored in the system and we ended up with no energy stored in the system. So effectively, if our current was 0 to begin with, everything is 0 at all times and math is great. Unfortunately, we have to take into account other cases where we actually turn the damn thing on. So let's go a little bit further, right? So E to the st can approach 0 if S happens to be negative and we wait a long time. Not really what we're looking for either. So the only option then is for this bit here in the middle, which is our characteristic equation, if this is equal to 0. So what value of S will force this middle part to be 0? Negative R over L. So S must equal negative R over L. Okay. So coming down a little bit here for our guess, we now believe it to be of the form A e to the negative R over L times 5. So how do you think we're going to figure out what the value of A is? Anybody have any thoughts? So, okay, so at t is equal to 0, we have IL of 0 is simply equal to A. So that allows us to figure out what that is. All right. So what is our inductor current at 0? So our inductor current at 0 minus was IS, but we're in the transient condition where we're at 0 plus and greater, right? So we need to figure out what IL at 0 plus is. Anybody have any thoughts? You should. The current flowing through an inductor cannot change abruptly, meaning whatever value it has at a particular instant of time approaching from the left has to be the same value approaching from the right. So IL at 0 plus has to be the exact same thing as IL at 0 minus, or we are literally violating the laws of physics by allowing an infinite amount of energy transfer to occur. So IL at 0 plus will be equal to IL at 0 minus, or IS. So in general, then, we can say IL of t will be equal to IL of 0 plus e to the minus R over L multiplied by time. So in a system like this, we expect the inductor current to experience an exponential decay, and the rate of decay is determined by the resistor and inductor values in the system. So coming back up here to our graph, we're expecting to see something like this, where this is IL at 0 plus e to the negative R over L times time. So this is how literally every RL circuit will behave if the circuit experiences a change. Okay. So now let's take a crack at an RC circuit. So let's say that we have a circuit wherein we have a voltage source connected to a resistor and a capacitor like so. I am going to define my capacitor voltage. Yes, ma'am. No. No, so the type of source that we are using to excite the system at t is equal to 0 minus and before literally does not matter. We're only concerned with what the shape of the voltage across the capacitor waveform is going to look like and what the shape of the current flowing through the inductor is going to look like. It doesn't, those elements don't care what they're connected to. No, so let me explain, right? So the reason why I couldn't just simply flip that switch up to disconnect the current source was because the current needed somewhere to flow, right? So I need a closed path for the current source to supply current to. For the voltage source, it doesn't matter. Disconnecting a voltage source is just going to give me an open circuit. It doesn't matter because I'm not concerned about the current flow. All right, so we have a similar situation here. Assuming once again that our switch has been closed for a very long time, it should be pretty easy to see that our capacitor voltage for t is equal to 0 minus is going to be simply Vs, right? Because when that switch is closed, all three of those elements are in parallel. So all of them have to have a voltage drop of Vs over them. Okay. Since our capacitor has some voltage drop over it at t is equal to 0 minus, that means at that particular point in time, it has some amount of stored energy. And once that switch opens up, disconnecting the voltage source from the RC network, we will see that the capacitor will distribute its stored energy to the resistor. And a very long time in the future, after the switch has changed states, we should see that VC at infinity goes to 0 because all of the stored energy has been transformed into heat by the resistor. So once again, we're trying to figure out what the heck is going on in that middle section, right? Hopefully at this point, we have a pretty good idea it's going to be some sort of exponential function. Why wouldn't it be if that's how the inductor behaved? That's probably how the capacitor is going to behave as well, but we'll mathematically prove it once again here. So I'm going to call this current IR, and this current IC, so that during the transient condition, for 0 plus is less than t is less than infinity, our circuit looks like this. Here's our voltage source. We have an open circuit because our switch is open. Here's our resistance R. Here's our capacitance C. Here is VC. Here's IR. Here's IC. And applying Kirchhoff's current law, we can see that IR plus IC is equal to 0. Using Ohm's law, IR can be expressed as VC over R, and IC can be expressed as C dV by dt. And we once again have a homogeneous first order differential equation, which, based on our experience from 5 minutes ago, a very educated guess for the shape of the capacitor voltage response would be AE to the ST as well. So if we plug this in, we're going to have 1 over R times AE to the ST plus SC AE to the ST is equal to 0, or A times 1 over R plus S times C times E to the ST is equal to 0. So what value of S makes that characteristic equation 0? Actually, hold on. I wanted to make sure we remember to include the negative sign up there. I got worried really quick. Go away things. There we go. Yep, absolutely right. So VC of t will be of the form something e to the negative t divided by RC. What do you think that something is going to be? It will be VS in this case, but generally speaking, what will it be? Exactly right. VC at 0 plus, which is the same thing as VC at 0 minus, but I'll talk about why I'm using that terminology in a minute. Let me scooch this over a little bit. So we see that capacitors obey an exponential decay wave shape very similarly to inductors, except that for the RC circuit, the rate of decay is determined by the resistance and the capacitance. So these two things are incredibly similar to each other, and electrical engineers are lazy and don't care whether or not we're using a capacitor or an inductor as an energy storage element. So we've actually created a concept called the time constant to characterize these circuits so that we can use one generic equation to literally solve any of these things. So let's talk briefly about what a time constant is here. So if I have some signal, let's call it y of t. And it is an exponentially decaying function. I wish I could draw this curve better. Let's normalize this guy right here and call this 1. Okay. So a time constant to an electrical engineer, and this is not going to be to scale, tau, is when our signal has decayed to a level of e to the -1 times its original value. Okay. So I'm going to make a table right here. Well, let's call this y, no, actually, t on this side, and y of t divided by y of 0 on this side, which is just going to be a fraction, right? So at 1 tau, we're going to have e to the -1, which I believe works out to be somewhere in the ballpark of 37%. I'm going to use my calculator to figure it out really quickly, because I don't remember what all these fractions are off the top of my head. 36.788%. So 2 time constants will be how long it takes for our signal to decay to e to the -2 times its original value. Or 13.534%. And 3 time constants will be down to e to the -3, or 4.979%. And 4 time constants will be at e to the -4, or 1.832%. And in 5 time constants, will be at e to the -5, which is 0.674%. So it takes a signal 5 time constants to decay from 100% down to less than 1% of its original value. So 5 time constants is what electrical engineers consider to be infinite, because we're saying it's fully discharged, whatever it is. Okay. So for an RL circuit, our time constant tau is simply L over R. For an RC circuit, our time constant characterizes the decay is R times C. So using this representation of a time constant, we can say generically that y sub n of t, so this sub n is the natural response, which is what we're talking about today, of any voltage or current in a first order circuit will be of the form Y at 0 minus, for t less than 0 minus, and it'll be Y at 0 plus e to the negative t over tau for t greater than or equal to 0 plus. So this single equation is all that you will need to figure out how any current or voltage in a first order transient circuit behaves. Okay? Now we derived it specifically for inductor currents and capacitor voltages, but it will work for literally any voltage or current because Kirchhoff's current law and Kirchhoff's voltage law have to be satisfied. So effectively, if one of the signals in the circuit is an exponentially decaying thing, then all of them have to be. Okay. We'll mathematically show that later. Okay. So with this equation as our baseline, let's work a couple of example problems and then show how this is done. So I've just gotten a random circuits textbook out of my office, and I'm just going to choose a problem. So the circuit that we are going to analyze, that one's boring. This one's okay. Will be this guy. We have a 6-volt source. Our switch is closing or changing from being closed at A to being closed at B at T is equal to 0. Here we have a 12 kilo ohm resistor. Here we will have a 100 microfarad capacitor. Here's a 2 kilo ohm resistor. Here's a 4 kilo ohm resistor. And we are going to be interested in determining the capacitor voltage as a function of time. Let's also find this resistor voltage as a function in time. And I'm trying to decide whether or not I want to find a current as a function in time as well, but we won't worry about that. Okay. So this is the circuit that we are going to analyze. So I am going to now impart to you my multi-step algorithm for doing these types of circuits in order to get the correct answer 100% of the time. Okay. So our first step will be to analyze the circuit at T is equal to 0 minus. So at T is equal to 0 minus, we are at DC steady state, which means our capacitor is going to look like what? An open circuit, and our switch will be a short between terminal A and that leg of the 12 kilo ohm resistor, all right? So at T is equal to 0 minus, this is what we have. 6-volt source. $12 kilo ohm resistor. Here is VC at 0 minus. 2 kilo ohm resistor. 4 kilo ohm resistor. Here is VR at 0 minus. And just for the sake of argument, I'll draw this open circuited thing here that actually isn't doing anything. That's correct. So at T is equal to 0 minus, the switch is still closed at A. T is equal to 0 plus represents the point in time where the switch has closed at B. Yes. And just, I understand that sometimes these switch directions and things like that can be a little bit confusing. So on the exams and stuff like that, I usually write the switch has been closed for a long time and opens at T is equal to 0 or something like that to textually let you know what is going on in the circuit as well so that there's not any confusion. Elizabeth. Because we're at DC steady state, and in a DC circuit, a capacitor behaves like an open circuit. Right? So if the current isn't changing, then let's see, actually, hold on. Yeah, no, so I is equal to C. Let me write it down over here so I don't screw this up. The current flowing through a capacitor is equal to C dV by dt. Because we are at DC steady state, dV by dt is 0, which means the current flowing through the capacitor has to be 0, so we can treat it as an open circuit. So at DC steady state, so at T is equal to 0 minus, and T is equal to infinity, which is what we're going to be doing on, what day of the week is today? Friday? Monday, we'll be doing forced response and all that kind of stuff. So we're going to have to look at the circuits at T is equal to infinity. Those are going to be our DC steady state conditions. So we're always going to use an open circuit for capacitors and short circuits for inductors. All right, so we need to analyze this circuit and figure out what VC at 0 minus and VR at 0 minus are. Anybody have any thoughts on how we might do it? So I'm just throwing this out there just for no reason whatsoever, but hey, this looks like a voltage source in series with a bunch of resistors. So maybe voltage division would get us what we're looking for very easily. Just thinking out loud for no reason whatsoever at all. How about we try voltage division? That sounds like a great idea. Thank you for the suggestion, Emily. So we can use voltage division for both of these voltages, right? So VR at 0 minus is going to look like 6 volts times, we're looking for the voltage drop over the 4 kilo ohm resistor. So that's going to go in the numerator, and then in the denominator, we have 12 plus 2 plus 4. So let's see. So that is 4 over 18. My math is right. So 24 over 18. 12 over 9. Did I do my mental math correctly? If not, please tell me. Oh, I can simplify that further as 4/3. Yeah. Well, anybody have a problem with that being the voltage drop across my resistor at 0 minus using voltage division? So, sorry, VC at 0 minus I can also get using voltage division if I take into account that the voltage drop across the capacitor is just the voltage drop across the 2 kilo ohm resistor plus the voltage drop across the 4 kilo ohm resistor. So that's going to look like 2 kilo ohms plus 4 kilo ohms over that same denominator. So 36 over 18 is 2. So anybody have any questions, comments, or concerns about the analysis that we did here? Right. So I happen to use voltage division because this circuit is literally screaming use voltage division at me. But if you guys aren't comfortable with that, you could have simply written the KVL equation since it is a single loop circuit, figured out what the current flowing around that loop is, and then used Ohm's law to figure out both of those voltages as well. I'm sure some of you are saying mesh. Mesh is the same thing as KVL here because there's only one loop. So, and KCL could also be done if you were a glutton for punishment and wanted to write a whole bunch of very easy equations. But anyway, or nodal analysis, I guess. So, are we okay with what I have done here? Anything seem not groovy? All right. So now let's look at step number 2. Now we are going to analyze the circuit. At t is equal to 0 plus. Okay. So at t is equal to 0 plus, let me scroll up here. Our switch has changed states. So now the left leg of the 12 kilo ohm resistor is connected to that terminal B, and the 6 volt source has effectively been disconnected from the network containing the resistors in the capacitor. Okay. So we're going to have something like this. I am intentionally not drawing the capacitor right now because I want to talk about what that's going to be in a moment. This is going to be VR at 0 plus. So right now, I'm just putting a question mark where the capacitor is. So let's talk our way through this. So what do we know about capacitors? The voltage drop across a capacitor cannot change abruptly. Okay. So whatever voltage the capacitor had at t is equal to 0 minus, it must have the exact same voltage and polarity at t is equal to 0 plus. So at this very specific instant in time, we know that there is a 2 volt drop across the capacitor, regardless of any other information. So I argue that at this very specific instant in time, the capacitor is behaving like a 2 volt voltage source because the voltage is fixed and whatever amount of current needs to be flowing through it can flow through. Okay? So what we're going to do at t is equal to 0 plus here for any circuit where we have a capacitor is we are going to replace the capacitor with a voltage source that has the same magnitude and polarity as what we saw at t is equal to 0 minus. So this 2 volt source, once again, is representing the capacitor at this specific instant in time because the voltage drop across the capacitor is fixed. It cannot not be 2 volts in this case, or we will literally be violating the laws of physics. Okay. As a little reminder here, I am going to write that VC at 0 plus is equal to VC at 0 minus is 2 volts, right? I don't have to find that. I know that has to be true. Okay? So the only piece of information that I need to determine now is VR at 0 plus. So what should that be? Voltage division again, why the heck not? So 2 volts times 4 kilo ohms over 2 kilo ohms plus 4 kilo ohms. So that's 8 over 6 is 4 over 3 again. Yeah. Seems reasonable. It's going to work out like that in this particular case because those resistors are in parallel with a capacitor. And since the capacitor voltage couldn't change, the voltage drop over that combination of resistors couldn't change either, but that will not always be the case. So for this specific circuit, it works out to where this voltage didn't change. Okay. All right, so anybody have any problems with the analysis that we did here at t is equal to 0 plus? Fairly straightforward, right? Okay. So what I'm considering here is us getting in the habit of analyzing the circuit at t is equal to infinity now, which is something that we're going to have to do later or not. Jim, I'm going to put it down here. But until we get to the problems that we're going to start working on next Monday, this is obviously just going to be 0 for everything. Okay. So I'm going to put an asterisk here because this step for what we're doing right now truly is not necessary, but it will be when we analyze different circuits. So at t is equal to infinity, we're still, the switch is still closed at position B. But our circuit is once again at DC steady state, meaning that our capacitor it looks like an open circuit. So we should very easily be able to see that VR at infinity is 0 volts. And VC at infinity is also 0 volts because there's literally no sources connected to the resistor and capacitor network that would make it be anything other than 0. So much like I described verbally earlier, at this point in time, all of the energy that was stored by the capacitor in this case has been transferred to the resistor. And so there can't be any voltages or currents in our system because that would imply that there's still energy left in our electrical energy left in our system. Right? Step number 4. Will be to determine the time constant of the system. Okay. So what we are going to do is we are going to determine what is effectively the Thevenin equivalent capacitance of the system during the transient condition and the Thevenin equivalent voltage of, the Thevenin equivalent resistance of the system during the transient condition. Now, I would argue that since there's only one capacitor, figuring out what the equivalent capacitance is going to be pretty darn easy here, right? It has to be whatever the hell I wrote way at the beginning. So I firmly believe that our equivalent capacitance is 100 microfarads by inspection, because it literally couldn't be anything else. Okay. Now, to determine our Thevenin equivalent resistance, we need to use the rules of finding Thevenin resistance, which means we need to be looking at a dead network. So our 6-volt source is turned off. We are trying to determine tau during the transient condition. So in that case, that means when the switch is closed at position B. Here we have our 12 kilo ohm resistor. Here we have our 2 kilo ohm resistor. Here's our 4 kilo ohm resistor. And what we are doing is we are finding the Thevenin equivalent resistance with respect to that energy storage element, which means we take the capacitor out and look in through the terminals that our capacitor left behind. So what is the resistance that we see? So I hear 12, 4, 8, lots of things. Nobody's giving me any math. I would argue that this takes at least a little bit of math. 12 in parallel with 6. Right? So 12 times 6 over 12 plus 6. Four kiloohms. Putting these results together, our time constant is REQ times CEQ. So if I multiply 4,000 times 100 micro, so 100 times 10 to the minus 6, I get 0.4. What should the units be here? So it should be seconds. The reason being, well, there's two reasons. First, the time constant represents how long in time it takes for the signal to decay to some specific value. So it would make sense there. And then also, if we look at resistance, that is an ohm or a volt per ampere. Capacitance is measured in farads, which is amp seconds per volts. So volts per amp times amp seconds per volts gives us seconds. So either way you slice it, this is a measurement of time. 0.4 seconds. And as you'll see why in a moment, the inverse of tau. So that is 4/10. So this will be 10 over 4 or 2.5. Let me make sure that 0.5 looks more like a 0.5 per second. Right. You don't have to do that part right there, but I do it, and you'll see why in a moment. So our last step is simply to plug information into our generic equation. So to remind you of what that generic equation is, the natural response Yn of t is y at 0 minus for t less than 0 minus, and y at 0 plus e to the negative t over tau for t greater than or equal to 0 plus. So let's look at our capacitor voltage here. What was the voltage drop across the capacitor at t is equal to 0 minus? P volts. What was the voltage drop across the capacitor at t is equal to 0 plus? Also 2 volts. That negative 2.5 is t divided by tau. So that's why I choose to do the inverse of tau as well, so that I can make it look pretty instead of having t divided by 0.4. I don't think it looks nice. So just for the sake of argument, knowing that this is the capacitor voltage, if we wanted to find the voltage drop across that resistor up here, without ever having taken any information regarding VR, we could simply find VR by applying voltage division, right? So using voltage division, VR of t is going to be equal to VC of t times 4 kilo ohms over 2 kilo ohms plus 4 kilo ohms. So that's just multiplying everything by a factor of 2/3, right? So that would be 4/3 of a volt for t less than 0 minus, and 4/3 e to the minus 2.5 t volts for t greater than or equal to 0 plus. We get literally the exact same result if we plug in values into our generic equation. Now, there's no need for us to actually do that circuit analysis that I did there, even though it was trivial as doing voltage division. If we keep track of all of the pieces of information at the different points in time, we can use that generic equation, even though we derived it only for capacitor voltages and inductor currents, for literally any voltage or current in our system, because KCL and KVL have to be true, right? So we know that if the voltage drop across that capacitor is of that exponentially decaying form, then the current flowing through the 2 kilo ohm resistor and the 4 kilo ohm resistor have to be of that exponentially decaying form because of Ohm's law. And then using Ohm's law again, the voltage drop across either of those voltages will be of that same exponentially decaying form, right? If one thing behaves like the exponential decay, all of it does. It will either be 0 or the exponentially decaying. All right. So this was an RC circuit, yes. Yeah, I mean, 0.4 is 4/10, and so I flipped it over to the 10/4. Yep. And that's just because I don't like having t over something. I like having t multiplied by something because it looks nicer to me. I don't care how you do it. That looks pretty to me, so that's why I do it. Okay. All right, so let's take a crack at a RL circuit, and then I will be done ranting at you for the day. So let me find one here. This looks like something. I just want to give you guys a warning that in this textbook, this problem has a lightning bolt, which supposedly means that it's hard. So I thought about throwing you guys a curveball here, but I'm not going to. I'm just going to explain something. So in this problem and in some of your homework problems, as I have it currently written, we're only interested in the voltage drop across the resistor. But we are going to have to know what's going on in the inductor as well in order to correctly redraw the circuit at t is equal to 0 plus, okay? So even if you're not explicitly asked for it, you are going to need to pay attention to what the energy storage element, if it's an inductor or a capacitor, it doesn't matter which, you're going to have to pay attention to what that is doing at t is equal to 0 minus in order to solve what's going on at t is equal to 0 plus. Okay. I just want to be really clear about that. I have recorded myself saying. So this is a circuit that we are going to analyze. Even though it is an RL circuit, we are literally going to do the exact same 5 steps because our formula doesn't care if it's an RL circuit or an RC circuit. Okay? So our first step, once again, is to analyze this circuit at t is equal to infinity, or excuse me, t is equal to 0. Minus. So at t is equal to 0 minus, our circuit looks something like this. Short circuit here is representing our inductor because at DC steady state, an inductor behaves like a short circuit. Here is IL of 0 minus. Here is VR of 0 minus. So you guys tell me what's what. What was that, Caleb? What will be 0, to be clear? I agree. VR of T should be 0. It's to the right of the short circuit. So I am perfectly fine with you saying VR of at 0 minus is equal to 0 volts at this particular instant in time. What's IL going to be? Five milliamps, yeah, because all of the current that's leaving the 5 milliamp source, let me draw a little thing here. All of the current that's leaving the 5 milliamp source flows through the 5 kilo ohm resistor, then it sees the short and turns back around. I was going to be mildly frustrated if you guys suggested mesh, when you can look at the damn thing and see, would mesh work? Absolutely. But it's so much more math than is necessary than just looking at the damn thing. So that's why I would have been very frustrated. Oh, sorry, you're right, 5 milliamps. Yeah, thank you. That's pretty good. All right, so anybody not okay with us determining these two quantities effectively by inspection for this particular circuit? All right, so if we're all okay with this, if you guys want me to give you 10 minutes so you can go do mesh, I'm not going to do it. You can. But if not, let's move along to T is equal to 0 plus. What was that? Yeah. So at T is equal to 0 plus, the 5 milliamp source and the 5 kilo ohm resistor are going to be disconnected effectively from the network. Actually, let me look at how this switch was drawn. So, sorry. So once again, for this exact moment, I am not yet ready to draw what's going on with the inductor because I want to talk about it briefly. So we know that the current flowing through an inductor cannot change abruptly. So whatever current was flowing through the inductor at T is equal to 0 minus has to be the same as the current flowing through the inductor at T is equal to 0 plus. So there has to be 5 milliamps of current flowing through the inductor in the indicated direction. Right? So I am going to replace inductors at T is equal to 0 plus with current sources for the exact same reason that I replaced capacitors at T is equal to 0 plus with voltage sources. Emily, I'm going to help you. Doesn't matter, but sure. We know IL at 0 plus has to be IL at 0 minus is 5 milliamps. And now we need to figure out what VR is. So how are we going to do that? Mesh is actually reasonable here. I would argue that you can do it with a convoluted form of current division, but mesh would probably actually be easier, at least make a little bit more sense. So let's call this mesh 1, this guy 2, and this guy 3. So we have a current source, so we're going to have a current relationship. So I can see that I1 minus I2 is going to be 5 milliamps. And now I'm going to write a KVL equation around my super mesh. So that's going to look like 1 kilo ohm times I1 plus 2 kilo ohms times I2 plus 2 kilo ohms times I2 minus I3 is equal to 0. And then we'll have 2 kilo ohms times I3 minus I2 plus 1 kilo ohm times I3 plus 1 kilo ohm times I3 is equal to 0. Solving this for I1, I2, and I3. It'll take me just a moment here. So let's see, our coefficient for I1 is 1, our coefficient for I2 is -1, coefficient for I3 is 0, 0.005. Coefficient for I1 in the second equation is 1,000. Coefficient for I2 is 4,000. Coefficient for I3 is -2,000. Coefficient for I1 in the third equation is 0. Coefficient for I2 in the third equation is -2,000. Coefficient, 0, -2,000. Coefficient for I3 is 2,000 plus 1,000 plus 1,000. Looks like 4,000 to me. Constant term is 0. I get 3/800 amps for I1, -1/800 amps for I2, and -0.625 milliamps for I3. Yes. 3. Anybody else get these results using their system solvers on their calculators? Always a chance I made a mistake. So. Yay, nay, good, all right. For whatever reason, my calculator didn't give me that last one in a fraction. It gave me -0.000625, which I know to be 0.625 milliamps. Yep. Because I put in my currents, so this current in milliamps was 0.005 amps. And because I put in all of my resistor values in ohms, I knew that the mesh was going to give me answers in amps. Yeah. All right, so from here, VR of 0 plus is just going to be I3 times 1 kilo ohm, right? Which should be -0.625 volts. Anybody have any problems with the analysis that we've done at t is equal to 0 plus? All right, so we're going to skip the analysis at t is equal to infinity because I know for sure that everything is just going to go to 0 here. So that's just kind of a waste of time. Now we need to figure out what our time constant is. Okay, so finding tau, I very strongly believe that LEQ is 1 millihenry because it is literally the only inductor in the circuit. So now let's figure out what REQ is. So I need to be looking at a dead network. So my 5 milliamp source looks like an open circuit. Here's my 5 kilo ohm resistor. Recall, and it's very important that we're looking at this during the transient condition, which means our switch is closed down like so. Then we have our 1 kilo ohm resistor. Here's a 2 kilo ohm resistor. Another 2 kilo ohm resistor. 1 kilo ohm. 1 kilo ohm. These terminals that I'm drawing right now are where our inductor was. We take the inductor out and we look into the terminals left behind by the inductor because we're trying to find the Thevenin equivalent resistance with respect to the energy storage element. Okay? So looking in, what do we see? So I see 1 kilo ohm in parallel with 3 kilo ohms. So the 1K and the 1K on the right-hand side are in series. So that makes 2 kilo ohms. That is in parallel with a 2 kilo ohm resistor. So 2K in parallel with 2K looks like 1K. That's in series with the 2 kilo ohm resistor in the top middle. So that's why I have 3 kilo ohms on the right-hand side, 1 kilo ohm on the left-hand side. So 1 in parallel with 3, which looks like 3/4 of a kilo ohm. From this, tau is equal to LEQ over REQ. So that is 1 times 10 to the minus 3 divided by 750. I wish this were a fraction. Let me think about this. .333, probably repeating, times 10 to the minus 6 seconds. So 1.3 repeating microseconds, or 4/3 of a microsecond. Yes, ma'am. What number? L divided by R. Tau to the minus 1 is 750,000 per second. And so finally, we're at the plugging stuff in phase. So y of t is equal to y of 0 minus, sorry, t less than 0 minus, and y of 0 plus, sorry, e to the negative t over tau for t greater than or equal to 0 plus. I hear whispering. If you have questions, by all means, ask, please. I understand that this is new. It might be slightly confusing. So for our inductor current, we're going to have 5 milliamps and then 5 e to the negative 750,000 t milliamps for t greater than or equal to 0 plus. For our resistor. We have 0 volts for T is less than 0. And then negative 0.625 e to the negative 750,000 T volts for T greater than or equal to 0 plus. Just by literally plugging in the previous the information from the previous steps into that generic equation. All right, so we have worked a RC circuit and we have worked an RL circuit. Do you guys have literally any questions about this material before I let you run free and work on the in-class assignment? All right, if you think of anything, let me know.